Welcome to the second lesson on the photoelectric effect. In our first lesson, we discussed what is photoelectric effect, what were the observations made from the photoelectric effect, and what were the conclusions given about the behavior of light or the nature of light based upon these observations. We learned some key terminologies related to this effect, for example, threshold frequency, work function of a metal. The phenomenon, just to summarize it overall, basically talks about whenever there is incident light or whenever there is electromagnetic radiation incident upon a metal surface, the radiations or the energy get absorbed by the electrons on the surface of the metal. And with the absorbed energy, the electron is capable of doing two things. Number one, it uses some of the energy to escape from the surface of the metal. And if there is additional energy that it has absorbed, this energy becomes the kinetic energy of the electrons. And we concluded that based upon what was observed, that what does the kinetic energy of the emitted electron depends upon, what does the number of electrons emitted depend upon, and we already discussed it in the lesson one, which actually helps us reach the conclusion that light possesses both particle and wave nature. Light or electromagnetic radiations are considered to be consisting of packets of energy called photons. So when a single photon absorbed by a single electron, the total energy of the photon basically gets split into two parts or does two things or can be understood to be doing two things or to be made up of two parts. One, the work function, which is the energy needed by the electron to escape from the surface of the metal, and the kinetic energy of the electron. So today we are going to apply the principle of conservation of energy to the whole phenomenon. So how can we apply? What equation can we write? We can write that the total energy of a photon is equal to work function of the metal plus kinetic energy of an electron. And we have to keep in mind that in the entire process, there is always interaction between one photon and one electron at a time, which means a single electron is only capable of absorbing a single photon at a time. And if this single photon that has been absorbed by the electron has enough energy to provide for the work function energy of the electron, only then the electron will be able to leave the surface of the metal. If the energy of the photon is less than the work function energy, then the electron will not be able to be ejected out or leave the surface of the metal. Hence, there will be no photoelectric effect. Uh, Therefore, there is a very important role that the frequency of the photon plays in here. Energy of a photon, as you can see on the screen right now over here, can be said to be can be given by an equation E equals h nu, or you can even write it as E equals hf simply, where f is the frequency of the photon. So the greater the frequency of a photon, the greater the energy it carries. So basically, how much energy a photon is capable of transferring to an electron is directly dependent upon the frequency of the radiation or the frequency of the photon or the frequency of the radiation to which the photon belongs. The work function of the metal is represented by a symbol phi, and the kinetic energy of an electron, as we always use kinetic energy, is given as half mv square. So if I try to create an equation using the principle of conservation of energy to this whole phenomenon, I end up creating an equation which looks like this. Energy of the incident photon is equal to work function energy of the metal plus maximum kinetic energy of the electron. And in symbolic form, this is how the equation looks like. Energy of a photon, hf. H, by the way, we did not speak about it. H is a constant. It's called the Planck's constant. Hf equals work function energy plus half mv square, or the kinetic energy of electrons. So hf is the energy of the photon, where f is the frequency. H is a constant known as Planck's constant. It has been named after a famous scientist called Max Planck. Work function energy is represented by a symbol phi. And by the way, in the entire equation, each of these quantity is energy, so has the unit of energy, which means it could be joules, or there is an alternative unit of energy that we will soon study called electron volts. Kinetic energy of electrons is given as half mv squared. Now, this is how the equation looks like. Hf equals phi plus half mv square. Now, I'm just going to manipulate the equation a bit and rearrange it, and I will make the kinetic energy. So I will just write kinetic energy of the electron. I'll make it the subject, and I'll move all the other terms on the other side. So kinetic energy is equal to energy of a photon minus the work function. So I just moved the work function on the other side of the equation. Why did I do this? I wanted to write this equation in the form of the equation of a straight line, which is y equals mx plus c. So my y quantity is the kinetic energy of the electrons. My x quantity is the frequency of the photon or the frequency of the radiations. In this case, now, if I plot a graph between the kinetic energy of electrons versus the frequency of the incident photon, I will be able to see how does changing the frequency of the incident radiation change the kinetic energy of the emitted or ejected electrons, provided that we use the same metal every time. Using the same metal means the work function remains constant. So the work function over here is basically a constant, and according to our equation, it has to be the y-intercept. So, and it is a negative y-intercept, which means it will lie somewhere here in the in the negative side of the y-axis, somewhere here. So, as expected from the form of the equation, by comparing it to y equals mx plus c, the kind of line I expect is a line with a positive gradient and a negative y-intercept. So, I expect to get a line like this. Now, in this line, if I find the gradient of the gradient of the line should be a value equal to the Planck's constant, right? And the point at which the line crosses the x-axis, which means when the kinetic energy is zero, this value at which kinetic energy is zero should actually give me a value of frequency. Which frequency should it be? The frequency, the minimum frequency needed for an electron to be ejected from the surface of the metal has to be an energy at which the minimum energy is provided, which is just enough to make up for the work function of the metal, even if the electron has no kinetic energy, but at least it is capable of getting ejected even with zero kinetic energy. So the frequency value at which the line intercepts or cuts the x-axis is the threshold frequency, the smallest frequency possible that a photon may have, should have, for an electron to be ejected from the surface of this particular metal with a certain work function of phi. So from the same graph, we can get the value of threshold frequency as the x-intercept. We can get the value for work function as the y-intercept, and we can get a value for the Planck's constant as the gradient of the graph. So having a look at the graph, we can see this. On the y-axis, we have plotted kinetic energy of the electron. On the x-axis, we have plotted frequency. So basically, we are seeing how does changing the frequency of the incident photon change the kinetic energy of the ejected electrons. And we can assume that if the photon that is incident carries a higher energy, because work function is not going to change, it's always going to be constant for a particular metal, as long as we are not replacing the metal with another metal of a different work function. If we have the same metal but we keep on making different photons incident upon it, by increasing the frequency of the photons, actually we have excess of energy that later becomes the kinetic energy of the electron. So it's a direct relationship, but we cannot really say that they are directly proportional. We know that the graph is not passing through the origin. So we can just say that the kinetic energy increases as the frequency of the incident photon increases, and the minimum value of frequency at which an electron can be ejected even without having a zero kinetic energy is known as the threshold frequency. And the value of the energy, the minimum energy which is required for an electron to be ejected, is known as the work function. And the gradient of this graph, like we saw by comparing our equation of conservation of energy with y equals mx plus c, the gradient of this graph comes out always to be a constant for if we do not change the metal, if we no matter for the same metal how many different frequencies we use, the gradient of this graph should always be equal to h. So these three things we have to remember. So just in case I present to you a graph where if you find the gradient, you get a value of the gradient which is not equal to h. And by the way, the value of h was given in the slide above. This h is a constant, obviously experimentally found by multiple repetitions. It is 6.63. The accepted value is 6.63 into 10 to the power minus 34 joules second. So if the value of the gradient is not 6.63 into 10 to the power minus 34 joules second, it means that our graph is not correct. Okay, so uh, basically, the value of h can be even experimentally. H is Planck's constant. The value of the Planck's constant can be experimentally determined by actually creating an experimental setup, which has very briefly been explained over here. So, what do? We have the photocell or the photoelectric cell, just like the setup that we saw Einstein had when he was studying the photoelectric effect. And if you remember, we had two electrodes, a negative electrode, which gives off electrons, or where electrons are ejected from, and the positive electrode to which the electrons move and complete the circuit. So imagine we want to calculate for each incident photon or each incident radiation of known frequency, we want to calculate how much kinetic energy does the ejected electron possess, so that we can plot a graph between kinetic energy and the frequency. Frequency is something which is known. Why? Because if you are making some electromagnetic radiations incident upon metal surface, definitely they are coming from a source, and we can always adjust or know the frequency of radiations from a particular source of electromagnetic radiations. So for a given frequency, how do we determine what is the maximum kinetic energy that can be possessed by the ejected electrons? What do? The positive electrode is now connected to the negative terminal of the battery. Negative means that now it is at a lower potential than the other metal plate, which is actually causing where the photoelectric effect is actually happening from where the electrons are being ejected. So when electrons try to move, the ejected electrons try to move towards this plate, which is now made negative, they get repelled. So they try to move with the gain kinetic energy towards towards this electrode, but they are repelled because of the electrostatic force of repulsion. So till the time that our voltage applied over here, or the energy per unit charge over here, does not become equal to the kinetic energy of the electrons, electrons will still keep on moving. So the electrons will only be completely stopped, the ejected electrons will only be completely stopped from reaching the other electrode, only if the electrical work done by this electrode becomes equal to the kinetic energy of the electrons, the maximum kinetic energy of the electrons. So we get this in an equation which looks something like this, that the kinetic energy, maximum kinetic energy of electrons, is equal to the electrical work done. Now this electrical work done may confuse you a bit at this point, because we haven't studied electricity yet. If you have already an idea of what this electrical work done is, very good. If not, then don't worry. Once we start our electricity chapter, we will learn about it. So basically it comes from the fact that potential difference or voltage, by definition, you have done it in IGCSE, potential difference is given as work done per unit charge. If the charge we are talking about is a charge of an electron, then the same equation can be written as work done per unit electron. Therefore, work done or electrical work done can be written as W equals EV. And work done has the units of joules, and so does kinetic energy of an electron. So how much work needs to be done by the electrode to stop the electrons from reaching it? The work that needs to be done by this electrode, the one which is shown curved over here, has to be equal to the maximum kinetic energy of the electrons. So since we can control the potential difference applied, how can we measure the potential difference being applied between the two electrodes? Just by using a voltmeter parallel to this setup, and we can actually determine how much voltage is being applied. This voltage applied, this, we can say, minimum voltage being applied to stop the electrons, that is just enough to stop the electrons from reaching there, is known as stopping voltage. And this stopping voltage, Vs, when multiplied by the charge of an electron, will give us the electrical work done on each electron, which will be equal to, just at the stopping point where the electrons stop moving towards this electrode, will be equal to the maximum kinetic energy of the ejected electrons. So at a particular frequency of the incident radiations, we can adjust the stopping voltage, we can keep on making it more and more negative till the ejected electrons completely stop from reaching the other electrode. We note down that voltage and then multiply it with the charge of an electron to get the maximum kinetic energy of electrons at that particular frequency. Then we change the frequency of the incident radiation and repeat the same process. And that's how we get a graph between the maximum kinetic energy of the electrons ejected at a certain frequency. And from this graph now, we can even find experimentally a value of the Planck's constant by finding the gradient of the graph. And also we can find the value of the threshold frequency by looking at the value of frequency when kinetic energy is a complete zero. Okay, so this is about photoelectric effect. And so this is the end of the lesson on photoelectric effect. Now in the next lesson, we are going to solve some exam style questions and see how to answer them.